So hi again, everyone, and welcome to the after show of the AI Hardware Show 2023, Episode 4. In this episode, we've covered 90% of the AI market with just one company. Sally. Elephant in the room.
Well, kind of. Hopper is really where we expect everything to go. Yeah. Almost all workloads will go to this Hopper architecture. So H100 is basically going to be the new A100. It's going to be everywhere, data center everywhere. So I think it's a really important one for us to discuss.
I mean, so we had V100, everything went to V100. Then we had A100, everything went to A100. H100 feels a little bit different to me in the sense that previously these launches we saw a wide launch at volume, or at least very quickly soon after. Whereas this time they're taking their time to come up to volume, and it's not because the chip is any more difficult than the previous generation, right?
Did they just announce earlier under pressure from the market? Who knows?
I know it's one of the things I've heard is that the DGX 100 system, the whole 8 chips in one.
Yeah.
That instead of being powered by AMD this generation, they're meant to be powered by Intel Sapphire Rapids, and Sapphire Rapids is late.
It's not ready. Yes, that's true.
So there's that. But also, they've only done one form factor. That's the SXM,
yes.
type OEM type module thing, and they haven't spoken about the PCIe cards yet in any great
Not
detail.
yet, but
we expect them.
We expect it to come. Yeah.
Yeah. I mean, we already have the Lovelace architecture, which is kind of similar for gaming. But yeah, it just feels like this one is kind of dragging its heels a bit. And I don't know if that's because Grace Hopper is really meant to be the inception point.
I see. Okay. So Grace Hopper in my mind is very much for HPC.
Only.
For HPC only, yeah, for
right.
Supercomputers and scientific kind of workloads. H100 I expect to see in hyperscalers and in regular data centers, enterprise data centers. So
for AI,
I think it's a slightly different market, slightly.
Well, okay, you say that, and I get why, but we saw Grace and Hopper being announced in, either one Grace to one Hopper, one Grace to two Hoppers.
So you can have different ratios of GPU to CPU. You have
but it's
the
more
Hopper super chip.
But it's more than just the add-in PCI card or DGX type system, isn't it? So I don't know. They have grandiose plans, but it hasn't coincided.
I wouldn't write them off. This is NVIDIA we're talking about, right?
Let's just
be realistic. I think this is going to be a smash hit. Personally, I can't see it any other way. So
does that mean that NVIDIA can price it to whatever they want?
Right now, I think it does mean that.
Even during what could arguably be a downturn in the chip industry, they can still price it sky high because everybody wants the last cent of value.
Absolutely, the sky's the limit. And if you already have all your code running on A100 and you want to upgrade, this is absolutely where you're going to go. So,
yeah, we're starting to see the first H100 supercomputers come in and bigger installations. But it feels like more of a just drawn out launch for me.
Yeah, it could be that the timing was different, or they announced earlier or something like that.
Supply of HBM3, maybe?
I wouldn't want to speculate on supply chain. But yeah, still coming soon. First half of 2023, I think.
Yeah.
So before you know it, it'll be here. We know they have silicon. I've seen it with my eyes, held it in my hands.
Tasted
it. Not quite. I'm not you. But they also have MLPerf results now for the training on Hopper,
this is true.
So we know it's real. It's up and running and working.
Yeah, it exists in some form.
It does exist in some form.
So, I mean, we're also going to get versions of Hopper down for inference, just like the A10s and...
Absolutely. I'd expect a full family, just like there is with the Ampere architecture, for sure.
Yeah. I don't know. Jensen, come on, give us a call.
Please come and be a guest on the show.
Yeah.
We'd love to have you.
So also in this show, just to go in order, I guess, neuromorphic, Intel Loihi 2.
Yeah.
And this is just one of those, kind of other chips that exists, but it's just so different. I mean, most of the neuromorphic chips are just different, right? So
it's very, very different. This is not, to be clear, this is not deep learning. This is not mainstream AI. This is like what's going to come next, basically.
Yeah.
So it demands a totally different computing architecture based on timing, which is just totally crackers, basically, compared to anything else.
It kind of makes sense because all of these neuromorphic chips, and we've got some more neuromorphic chips to talk about. Brain mimicry is, an interesting thing that gets people on board, investors, and
it's a great story. I'm on board.
Yeah. But the whole point about the brain is you have neurons and synapses that are chemical based. They have timing associated with the action, but also the action is a smeary mess and not a defined discrete point.
Yeah, it's so it's based on timing, and the timing at which the spikes, these are electrical spikes, and the timing where the electrical spikes arrive in the next neuron. And the part of the trouble is we don't know exactly how the neuron works in the human brain, so we have a reasonable idea, but there are still different models of the neuron floating about, different mathematical models for exactly what the neuron does when it receives the spikes.
Yeah.
So we know it kind of integrates the spikes in the mathematical sense. It adds them together till it gets to a threshold and then fire, but there are different variations on that, which, again, how realistic is it? Does it matter if we implement that in silicon or not, as long as it works in silicon?
Yeah.
So, yeah, there's a lot of research still to be done in this area.
So, I mean, spiky neural networks, perhaps the biggest spiky neural network installation is something called Spinnaker. That's been up in Manchester.
Yeah, this is going back a long way over the years. Yeah.
I've got in my mind 2008 or something for Spinnaker.
Sounds about right.
But then they've got, Spinnaker 2, and the whole point of, say, Intel's chip is let's do the equivalent of that supercomputer scale spiky neural network system, but do it in a box.
Yes.
That was Loihi 1 and Loihi 2. So the difference between Loihi 1 and Loihi 2, as I said in the episode, is we now have a better neuron to synapse ratio. It's improved 8-to-1. 6
so there's more compute, less memory.
Yeah.
In computing terms, yeah.
Yeah.
Well, there's the same amount of memory as there was in Loihi 1, but just more neurons, relatively speaking.
Which means you have many different ways to go firing.
True.
So
that's right.
So in standard ML, this may be deeper hidden layers or just bigger hidden layers with more connections.
Right.
So
they also added more programmability to the neuron, which allows us to copy different models of the neuron. They basically give the neuron an instruction set of its own this time around.
It's like configurable neurons.
Exactly. And then the spikes can have magnitude as well this time, which opens up some other avenues.
Especially, when you're adding in magnitudes to get to a threshold, I guess.
Yes.
It's. I remember speaking with Jim Keller from Thames Torrent about the capability of neural networks and the brain, right? So normally when we consider neural networks for machine learning, we're thinking about a 2D matrix array, right? And matrix or matrix vector, weights, activations, everything's 2D. And he was telling me that based on his reading, the brain, it's a 3D construct. And in the same way, it's also a 3D neural network. However, it's only about 6 or 7 layers deep. So when we're considering about these, wide array of computer chips, either from Thames Torrent, from Dojo, or even from places like Intel and Loihi, we think about this 2D array. But if we actually add an element of 3D, what does that give us?
Right. I know you're raising this because Loihi 2 has the ability to scale in 3D, which I think is going to be more brain-like.
Yeah.
But exactly what that is going to give us, I wouldn't like to speculate.
No, it's one of the. It's like a 10-year research program, right?
This is research, yeah.
So I mean, Loihi 2. It isn't a commercial chip in the traditional sense in which we're speaking about most of these companies. It's a research part. It's using Intel's 4-nanometer process. Yep. So one of their first EUV chips is about 35 square millimeters. I kept thinking it was 14 for some reason. But with these small chips, they're pipe cleaners for the manufacturing process as well. So when it comes to, the other products that they're going to produce on this process node, it just gives them a test chip to do that with. And it's just interesting that they picked Loihi and neural networks, and the other Intel 4 chip is blockchain. So that might give you some hint or something. So one company I've actually been getting emails about for years that we covered in this episode is Hailo.
Yeah, they've been around for a few years.
It makes it sound like a taxi hailing company.
It kind of. There was a London cab taxi hailing app called Hailo.
Oh, that's why.
With the same spelling.
That's
I think
why.
that's what you think of.
Yeah.
To be clear, this is not related to that.
Right. But Israeli startup?
Yep. So they have industrial applications in mind, automotive and industrial, which is kind of a subset in that you need like automotive grade, industrial grade chips. You need the temperature range, you need the reliability. There are added requirements over and above just the latency and power stuff that we talk about for everything else. So yeah, it's gaining those automotive qualifications as well is years and years and years of work, which they're now there, I think, which is fantastic. So I'm going to more like safety related automotive applications as well. So yeah, it'd be interesting to see where it ends up on what they do.
Well, it's ASIL B and ASIL D is what everybody talks about. I always forget which way round it is.
So D is the more stringent.
Right.
That's like the chip that actually turns the brakes on when you press the brake pedal.
Okay.
B is like, I don't know, camera that tells if you've fallen asleep or something.
I always think, somebody told me, you'll know which one it is because it's by design. And I was like, okay, B, by design. No, D, by design. Okay.
Yeah, okay.
Just trying to think which is retrofitted and which is designed for. Okay.
Right. Okay.
I remember I was speaking to a company on that front, and they're saying one of the issues is the high temperature range.
Absolutely, yeah. So for automotive, it's really serious, but for industrial, that applies as well, and vibration and stuff like that as well, right?
So the temperature range of a normal chip is like from 5 to 105.
Yeah.
Whereas industrial automotive, it's -40 to 150. Sometimes you'll see Intel chips be high temperature range, and that's all what they mean. But yeah, I was speaking to the company that's saying that apparently storage has a lot of problems with that temperature range.
Oh, right.
So you have to apply new technologies for things like whether you're using NOR or NAND flash or MRAM or ReRAM, and a lot of those technologies, while good for their individual applications, have those issues. So when we're speaking about AI, especially, when you still need the performance, you still need the power. Sometimes the minimum specification is simply the ability to do anything at all. Right.
Yeah, I guess so. It's like if you can meet the temperature requirements, then the other requirements are maybe slightly less, but I'd say in Halo's case, they're not worried. They have good performance, I think, for what they want to do, which is video analytics from various places around the factory floor, or industrial inspection, which is maybe a little easier, but you need really fast latency. And yeah, it's it sounds like a niche, but this is a huge opportunity, absolutely huge opportunity. So
I mean, industrial in itself is encapsulating one word, but we're talking trillions of dollars of any market.
Absolutely. Absolutely huge use cases. But I mean, think about like industrial robots that are building cars as they go past on the production line, something like that. There's loads of AI in there, not just for the movement, but for the safety features and stuff as well, right?
Yeah, well, you need them to be aware of where a machine is, not just functionally it's, over here every time.
Exactly. But then, when the person walks into that space as well, it's like, oh, now we have to stop.
Yeah.
Let's not brain him as it goes past.
I mean, so we have things like that, but I've also seen machines where you're like sorting apples and they're flying through the air, and then it detects a brown one and it pops it out. But it pops it out in a 50th of a second.
Yeah.
So
the latency of on the camera where the apples are falling by. This is a kind of
batch one
kind of thing we're talking about.
Yeah,
it's very stringent requirements.
It makes me wonder about that market. Is it high volume, low cost, or is it low volume, high cost?
So what I can tell you is gateway type of hardware is quite popular. So the AI might not be happening in the machine or in the camera. It might be somewhere else on the floor where they have lots of video streams coming in, and then they have lots of AI processing in that box, like an edge box of some kind, industrial edge box we call it. So Hailo has quite a few customers in industrial edge boxes.
Right, okay.
Long list, actually, of customers. So, I think they're already very well established in that market.
I do remember having a discussion, I think, with Intel, because they were talking about security camera AI, and I was saying, well, is the AI done per camera, or is it, or all the camera streams go into like a centralized edge server? Because then you have batch 1, and then you have, say, like batch N, batch 128, 256. And the chip you designed for those use cases is going to be different.
Sure, yeah, sure.
Not only just the power requirements, but the architecture.
Absolutely.
If it's a batch 256, then you're going to make, say, a bigger systolic array or what have you. Or if it's batch 1, you're going to optimize for latency in your SLAs. So,
yeah, it's a big opportunity, I think, not to put too fine a point on it. So I'm glad we got to talk about it here.
I'm sure they are as well. So into the second half of the episode, I started speaking and detailing SambaNova. And SambaNova itself is an interesting company. We've both covered them separately. And Marshall, if you're watching, hello.
Hi, Marshall.
Yeah, next time you're in London, respond to my messages this time.
Oh, ouch.
No, it's fine. So SambaNova was a weird one in the industry to begin with. I'm not sure how because we heard about them. I think they even sponsored an event that they never showed up at.
Oh, that was Grok.
Oh, that was
Grok.
Okay.
That was Grok.
Okay, we'll get to them in a future episode. But SambaNova for a while was very secretive.
Sure,
and they still are to a point.
They are a little bit reticent.
Yeah,
yeah. I guess so.
But they have $1 billion of funding. We got to know what they're doing, right?
Well, yes, we do and we don't. I think part of it is the desire to keep the story focused on the system that they want to sell. They don't sell chips. They deliver a rack to you, and it's all in one, basically. It's a slightly different proposition. Well, so you and I are really interested in what's going on in the chip. But maybe not SambaNova's customers, and maybe not.
It comes to that point. I have a similar thing with the smartphone space. I tell people I review chips, not devices. So I don't speak to any of the people that sell devices. I need to get the chip. I need to get the chip manufacturer to give me a device. But I totally get it from a marketing perspective, especially as we're moving forward into this decade. So whether you're speaking about AI, whether you're speaking about HPC, whether you're speaking about just standard enterprise, people are buying solutions.
Absolutely, yeah.
Not chips. So you do want that messaging to be solution focused. Again, so with Intel, Intel want to sell the CPU, the memory, the SSD, the networking, the GPU now, and they want to sell you the box with the software ready to run. I mean, we've spoken about Cerebrus in an earlier episode. They sell a system.
Yeah, it's a big box. They come and deliver it to you.
They still talk about the chip because it's a unique chip, but they sell the system. And the same with GraphCore. They sell you a system, not a chip. So I totally get where SambaNova's coming from. Still want to know about the chip.
I mean, still dead keen to know everything that's going on. They have spoken a little bit. We know it's a CGRA. We know they have lots of expertise in multi-threading and stuff. So I'm sure they do very clever things. We don't know all the details. I don't know all the fine details.
I mean, we know that they have a lot of defense customers.
Sure. We know they have a lot on enterprise as well. Yep. Financial, predicting the stock market and stuff. I don't know what they do. But the sell is then it's a group of data scientists, and you deliver the rack, and you can pretty much, SambaNova can supply the models as well and just plug it in and it all works. So
we saw the first generation product, the SN10. You saw the new SN30.
Yes, I did. Held it in my hand.
How big is this thing?
Well, I'm sure we can show the photo of it in my hand, but it's the size of a beer mat. It was the first word that came to mind.
Your words, not theirs.
My words, not theirs. Yeah, that's not part of their marketing.
So, okay, Marshall, if you're watching, and people who are watching who don't know who Marshall is, go look him up on LinkedIn. And what you need to do as a merchandising opportunity is sell SN30 beer mats. I will
want one. Yeah, I want one. I want that.
If you don't, I want the license to do it. But that's the package with the heat spreader. The chip is obviously smaller than that, but it's a massive chip, 86 billion transistors.
I think chiplets. We think chiplets in that massive thing. We think chiplets.
Maybe. We don't know. Again, they haven't told us. But 2 to 6x faster than the SN10. That's what they're promoting. And this whole concept of CGRA, I kind of want to dive into it a little bit. So, coarse-grained, reconfigurable array. Even though I've said it multiple times today, I'm still tripping up over it. It's kind of like an FPGA. So an FPGA, field programmable gate array, where you have a number of logic cells that you can either dedicate to memory or compute and do different things. And people use FPGAs to essentially validate chip design before they make it.
For prototyping,
yeah. So a CGRA has still that configurability, but at a slightly higher level. So you now have blocks of hardened memory and hardened compute, but that memory and compute can be configurable. So you end, I think with their SN10, they said 1,280 blocks, half of them compute, half of them memory, but configurable. And the point is, if you've got a machine learning problem where it's helpful to move the data kind of in a recursive fashion around the grid, then you get the power benefits of that. It's maybe not the best power efficiency that you may get with a very dense ASIC, but
you have that flexibility for the different data paths and the data flow that you need to best match the workload.
So I've been noticing that CGRA is popping up a lot more in AI hardware recently.
Yes. Okay.
So I spoke to MediaTek, smartphone chip manufacturer. They've got an artificial intelligence processing unit in their latest generation SoC. I was asking the question, so like, this sounds like a CGRA, and they go, you know what you're talking about.
Aha.
I was like, I'm
going to try that.
It is funny because traditionally when they do their deep technical presentations, they're not that deep or technical, from my perspective anyway, right?
It's all relative, yeah.
Yeah, and then so when you start asking about the actual architecture, they go, this person perhaps needs a separate briefing, and we're not going to tell him anything.
Yeah.
Unless it's under NDA.
Yeah.
And I also said that to Qualcomm with their chip. And they said essentially said we can neither confirm nor deny. And I was like, are you referring to the question itself or the fact that it's CGRA? And they said the question itself.
Oh my goodness.
It's very clear SambaNova have demonstrated that CGRAs can be really powerful.
Absolutely.
So when people are doing them, I think they want to be quiet about the fact that they're doing them.
It's a possibility, I suppose. Maybe the market's becoming more educated on what CGRA is and what it means, and that's a possibility of why we're starting to hear that a little bit more. I think they've always been there. It's always been an idea. Like, it's always been a thing. Maybe we just didn't know.
Or it's sort of to do with, say, a lot of the secret sauce may be in the software abstraction, right? Into TensorFlow, PyTorch.
Right. Crucial, obviously, yes.
So we've designed this series to be the AI hardware show, not the AI software show.
But software is absolutely crucial.
It's the next stage, and I think pretty much everybody is supporting 2 of either Caffe, PyTorch, TensorFlow or TensorFlow Lite, especially with the inference chips.
Yeah.
And more generalized frameworks like Ray and Onyx as well.
JAX, MixNet. There are other frameworks. There's loads. It's still quite fragmented, actually, but the main ones we're talking about today are TensorFlow and PyTorch, I would say, across most applications.
You can tell when companies have bigger plans for wider market adoption when they say TensorFlow, PyTorch.
Yes.
When they start talking about the smaller ones, they have specific customers in mind.
Yes, that's true.
So,
but if it supports Onyx, I think Onyx is a model format for portability. So I feel like that. Yeah. That's a good all rounder, right?
Yeah. I think Ray's kind of in that sort of situation as well. So, and then flipping back and forth between sort of trading and inference, Innatera.
Yeah, so I'm glad we got to put this one in the same episode as Loihi because it's also about spiking, but doing spiking in a different way. So for Innatera, it's analog. It's analog spikes. And Loihi, of course, is asynchronous digital, but it's still digital electronics. They just, it's just asynchronous digital. Analog is kind of a whole different ball game. It's making it all work properly. There's a reason we use digital electronics. Asynchronous digital is very hard to pull off, I think. There's not many teams or people in the world that can do that. But yeah, analog is, if you're a total purist on spiking networks, it's like the brain is an analog computer. So of course you want to mimic the brain as closely as possible, and maybe you want to do analog. There's tons of power to be saved if you can get it to work. And it seems like it does work. Certainly in this case, it's it's up and running and it's working. But yeah, it's a great story because the amount of energy that you use for the spikes is almost the same level as what you're actually using in the brain. So,
well, the brain's like meant to be this goop of about 20 watts, 25 watts,
something like that. We think, yeah. So it's very, very low power for the amount of compute that happens in the brain, and very sparse compute as well. And it's still a lot of this is still in the research kind of.
Well, when you have
phase.
Billions and trillions of, and we're talking about chips that only have millions or less than, right? It's just. Is it simply a scale issue? I know Intel at one point said we can simulate a mouse brain with essentially a couple of drawers full of chips.
Yes, they had a hamster brain, or a lobster brain is really small, 10,000 neurons or something. But yeah, these are basic animals.
But overall they're still taking hundreds of watts, at least digital hundreds of watts. Yeah.
Yeah, it's we're not quite there yet. Let's just say we're not quite there yet.
But the problem with this analog-based compute, whether you're talking spiking or low precision, is in the precision itself. I mean, you're relying on digital to analog conversion initially to do the compute, and then analog to digital conversion. And the accuracy of that is not ideal. I mean, so you can get 12-bit converters, but it's like a fuzzy 12-bit.
Yeah, I mean, it's not... With spiking, the information is encoded in the timing of the spikes. So it's not... So on the Innatera, for example, there's no magnitude to the spikes. It's purely all on the timing.
Right.
So we're not talking about like an analog compute where you have levels in the transistor or something where you're running a...
Okay.
It's not quite the same thing. It's like... It is a bit different, I think. With the timing, it's like... It has to be, obviously there's a level of precision with timing as well, like accuracy and timing, but it's not the precision that I think we're talking about here. Well,
it's the concept of a matrix multipliers.
Yeah, no. That's not what we're doing here.
So 98% of what 95% of what we're going to talk about on this show is digital,
absolutely,
deep learning,
absolutely.
Machine learning, whereas this is off in its own field.
It's completely separate to deep learning, and so a lot of it is still open research questions as we're talking about. But how do you train a spiking network, for example, is still an open question.
And how do you encode that in either an analog? It makes me think of the language map of Europe, about how all languages are related. And over here you've got Finnish, and over here you've got Hungarian.
Yeah, they're somehow related, right?
That's kind of what neuromorphic is right now, especially the spiking stuff.
Yeah, I mean, it's still AI, but it's not. It's still, you still train it. You still train the network. It's not in the same way, but you still train the network.
But you apply it to the similar problems as well.
That's true. Yeah,
so
that's true.
Audio, wake words.
It can even do
video.
Image. Person detection, person ID, even basic face recognition. Not Innatera, but other companies. Innatera is focused on time series data. But for other companies, I've certainly seen Face ID.
I've seen people try to apply it to like smells as well.
So one of the demos for Loihi 1 was a smell. Yes. It was detecting smell. So when we say smell, really it's like gas detection or detecting a compound in the air.
Yeah.
They call it smell because it sounds like... It sounds cool.
Well, so I mean, when I did my PhD, it was to do with electrochemistry, which is all about detecting chemicals. You have a chemical that lands on your electrode. You either exchange an electron, either give it or take it, and then you measure that current. And then, depending on the matrix or the chemical you have and the concentration, that's how you detect what you're trying to detect. And in this case, that electron transfer becomes a spike. But can you differentiate spikes of different compounds? Especially, the whole thing about electrochemistry is you've got to prepare your solution or your matrix of your active ingredient, and you've got to make sure your active ingredient is the only thing that interacts with your electrode. So you actually prepare the electrode, say, with nano gold, because you're working with a thiol or something, and sulfur binds very well to gold, and then you get your electron transfer. So, yeah, sorry, chemistry rant.
But we're a little off topic.
Yeah. But
the smell thing is cool.
Yeah. Smell differentiation, I think, is a bit more difficult.
So we're talking about sniffing for explosives in the airport, in people's baggage and stuff, or we're talking about sniffing for like dangerous gases in the air, carbon monoxide in the air or something like that, right?
Yeah.
It's this type of thing. It's not literally smelling food or something. Or
smell the concentration of how hot your food is.
Yeah, exactly. And we only need a silicon brain to do that.
Yeah. And so the last chip of this episode is a more generalized CPU chip, Ampere Altra Max. Ampere. I think
I'm saying Ampere. I don't know.
I'm saying Ampere.
Okay.
Neither.
Yeah, well, doesn't matter.
I've lived up north. I know how it goes. But so Ampere Ultra, or codename Mystique, went up to 80 cores. Ampere Max went up to 128 cores, around about 3 gigahertz, no turbo, consistent performance. Now, I included it in the AI hardware show because it's a high-dense compute platform that people are either using for AI or using as a host for AI. We saw back in 2021, NVIDIA validated it for use with its V100s and A100s, for use with CUDA and the acceleration that provides. I mean, one of the things we talk about is how these AI algorithms are developing. And especially, for example, in transformer networks, sometimes you want to do additional compute in between the layers of a neural network. And in a traditional system, you have to take the data from the GPU to the CPU, compute it, then put it back on the GPU to continue. Now, there are AI chips doing that and having the compute on die, but for something like an NVIDIA GPU, you still need to do that transfer. And this is where having strong levels of compute, for example, in Ampere Ultra, makes sense.
Yeah.
With that many cores, it does integer workloads really well.
Sure. I was just going to say that sometimes you need to fall back as well. If you come across an operator of some kind that your accelerator can't handle, sometimes you need to fall back into CPU.
Yeah.
Or, in an edge chip, it'd be an ARM core or something.
Yeah.
Kind of fall back onto it to make sure you can actually handle it. You don't just break.
Yeah. It's better to go slow than to stop.
Exactly, yeah.
Yeah. But Ampere Ultra's value adds that they keep talking about is density. So having, over 10,000 cores per rack. And then also they're leveraging this as a service model. So when you have 128 cores, you can actually do things like Android gaming at scale, especially when you add in, say, an NVIDIA GPU that can do this sort of multi-instance strategy.
Yes.
So now,
MIG.
Yes, MIG.
MIG.
Is it still only 7 instances?
Yes, I think they break it into 8 and then use one bit for control or something. So you can get 7 instances. And I believe the instances don't have to be the same size.
Yes. I mean, so on top of that, if you've also got, a strong compute platform, when you can supply 16 ARM cores to each of those instances, you get this mix of AI compute on both sides, especially for, again, those small microservice workloads that do some level of AI, right? It's that we're expecting to hear about Ampere's next generation chip, Siren, or they're calling it Ampere 1, sometime soon. I mean, I was hoping it'd be second half of 2022, though it's looking more like first half of 23. I've heard there are some reasons for that, none of them technical, but we'll get to see. It's I'm getting very clued in with their team, so I'm really looking forward to it. But in the same way that I'm looking forward to new CPUs from AMD, CPUs.
Yeah, absolutely.
I mean, I know in a couple of episodes we're going to be talking about Sapphire Rapids.
Yeah.
And that's massive for AI. So don't count CPUs out just yet.
Yeah, I mean, Intel loves to talk about how much data center AI still happens on Intel CPUs. It's the incumbent technology. It's what people know and what they like, and they like the flexibility as well. So AI accelerator is not for everyone, at least not yet.
Well, so we're talking about NVIDIA is like 90% of the market for training, right? Of the other 10%, a lot of that's still CPU.
It's all on Intel Xeon CPUs, yeah.
And then we look at the inference market, and a lot of that is on, or at least data center inference.
Yeah, it depends what it is.
But it's still...
so for recommendation for sure, because it's such a tricky one to accelerate. I think we're going to talk about this in a minute. But yes, recommendation for sure.
But it's still in that mid double digits for sure. So still lots of money going around on CPUs. So don't count them out just yet. So let's give that topic a round up there, because we've got to go film some more episodes. Thanks as always, Sally.
Thank you very much.